Okay, welcome to the Introduction to Data Wrangling course module. So this one is a module that covers parts of the tidyverse, including dplyr and reader packages. So we're going to use the various functions to manipulate, clean, and organize your data from messier raw data to something that's more manageable, summarized, or able to be visualized. The aim of this module is to teach the basic and commonly used tidyverse functions throughout the entire data manipulation process. I strongly recommend using the tidyverse functions over more base R functions because the tidyverse code is more widely used and is more user-friendly. It reads like text, and you can easily add code that compounds to create your data wrangling, data manipulations, etc. If you know anything about ggplot2, it's very similar to that, where it's like the grammar of graphics, it's the grammar of coding. It's basically us saying, do this to the data, then do this, using very cut and dry function names rather than obscure ones that a lot of base R ones aren't as intuitive. If you're interested in learning more about the tidyverse, I recommend Hadley Wickham's R for Data Science book. This link has the freely available version on his website for the second edition. It's also translated into multiple languages. So we have two data sets for today. The fisheries data for this module is from the long-term resource monitoring element of the Upper Mississippi River Restoration Program. And it's from USGS or US Geological Survey. If you choose to do the assignment as practice, it's gillnet catches from 1930 to 1932 in Lake Michigan. As for all documents that I am teaching from, this is an R Markdown document. Therefore, all text outside of code chunks is just text. None of it is code. Code is only provided in code chunks, and it can only be run in code chunks. If you're unfamiliar with R Markdown, refer to the R Markdown module to better understand this format. So we're going to get started with the reader package, which is reading and writing data. So it's part of the tidyverse that allows for easy import of a large variety of data sets without weird name changes or like weird header changes. Provides for a lot more specificity and user-friendly input than like the base R functions do. It creates what's called a tibble, which is a type of table that's easier to manipulate with the dplyr functions. Base R creates a data frame, which can lead to where many of those problems with importing data stem from. I want to note that for some packages that use base R functions, you might have to read in with base R's read.csv. I found issues with using the packages, specifically Cyber and MixSciR, that required the use of the base R read.csv rather than the tidyverse read_CSV. Sometimes you might get weird errors and you might not know what it is. Try this. Try using a different reading function if it's within the data itself. And it might just be a weird thing. All right, so for reading in your data, there are many different ways, many different data types you can read in. These are some examples. The base R function is read.csv with the file path name and the name of your data here. The tidyverse way is read_CSV. It'll be file path name with the name of your data as well. For semicolon delimited files, read_CSV2. Tabs delimited files, read_TSV. Any delimiter, read_delim, and then you put arguments in here to say which delimiter it is, colon, semicolon, space, whatever. Fixed width files, read_FWF, read a table, read_table. They're very straightforward. Now, what type of data you have should be clear from when you open it up in Excel or wherever you're opening it up. If it's comma delimited, if it's semicolon delimited, if it's tab delimited. A lot of times we're using CSVs, which are comma delimited. But a lot of times you might, or sometimes you might run across weird data formats, especially like fixed width files or tab delimited files from federal or state agencies if you're using their data. So use these other different reading functions. And you can write files using the following functions, and these are just a handful of them. For base R, it's write.csv, the name of your object your data is saved as in R, followed by the file path name and the name you're naming your object on your computer. For tidyverse, it's write_CSV. And again, what it looks like there is the name of your object you saved it as and the file path name with the new name of the CSV file. For some reason, if you have an Excel specific CSV, write_Excel_CSV. For tab delimited file, write_TSV. So basically the same as these, but it's write instead of read. And we'll get an example of this in a little bit for reading in the data. What's nice about using the tidyverse is it is reading like text. Do this to the data, specify this in the data. And we'll see that throughout today. You can add many arguments specifically to these reading and writing functions, including things like skip rows. So sometimes we have metadata at the top of the data. Whether you have a header or not, you can add new lines, how to denote your NAs. Maybe they're -999 in the data set instead of NA. Your column type, sometimes it'll read in things incorrectly. So for example, if you have numeric data that has a lot of NAs in it, it's going to read it in as a character, and we need it as numeric, so you can specify that. So we're going to use the fish community data set, the LTRM community from the upper Mississippi River. These data are U.S. Geological Survey data, and this is a subset of the data the fish community sampled in 2018. This is a very small portion of the data. First, we have to load our packages. So we're just going to load all the tidyverse functions right now. Library tidyverse. Here we're just getting our working directory. Week 2, intro to data wrangling. Okay, that is exactly where we want this. So our working directory we should be looking in a data folder, looking for this name of this data set. So this is our read_CSV function. So we have read_CSV. We're saving the data as an object called fish using this less than and a dash to make a little arrow. We are using the file path name because our working directory is in the folder week 2 intro to data wrangling already. We just need to go in the subfolder. So this period here says use the same working directory that this file is already saved in, which is this whole file path name. Then look in the subfolder data, and then find the file called 2018 ltrmdata.csv. So that's the rest of the file path name, including this with the period. Comma. Here we are specifying a column type. So I mentioned that sometimes if you have a lot of NAs in a data column, it'll read it as a character. This is one of those times where our weight column has a lot of NAs in it, and it's always going to read in as a character, but we want it to be numeric. So we say call_types for column types equals, and we could have many on here, list. Our weight column is just lowercase weight, and we're saying that equals call_double open parenthesis. This double in the tidyverse means numeric. Don't know why it's called double, but it means numeric. So it's call_double. So it's going to read in this weight column as numeric rather than a character. So we run this code. It just gives us a parsing issues. Ignore this for now. It's fine. I've still read in the data, and we can look at those data. 4,809 rows and 86 columns. It is a very large data set. and the columns and stuff. But we have a lot of information in here specifically. Okay. I wanted to do a quick aside. So when we read in these data, we asked R to read in this weight column as numeric specifically. However, if we didn't read these data in and the data came in for the weight column as a character, there are other ways to coerce the data into a numeric variable. And a lot of times we have to do this when we're visualizing data or just need to change the variable type for an analysis. So our aside is to look at coercion of data types. We talked about this briefly in the intro to R tutorial, but if you skipped that one, we're going to talk about it again because it is very important. So I cannot stress enough how important it is to look at the data class and mode and the data types for your different columns, especially when you're converting among these modes. So as an example for coercion, if you don't specify that data type when you read in your data, you can coerce those columns either with a function permanently for your R session or using wrappers, so within a line of code specifically. So this is not a permanent change for your R session. It's only changing it for the specified function. Haven't looked at ggplot yet, but what we're showing here is the wrapper. So fish code or species. Here we have too many columns to look at. We have fish code here, which is our species column. And we have 4 different or 6 different column or species names here. And they're 4 letters each. This is a character. But what if we want it to be like a factor, if we're doing factors instead of characters for something, for analysis, or for here, for plotting? What we can do is say, okay, here's our function. We're just going to wrap this wrapper of as dot factor around our column name. And it's going to make it a factor. And this is going to create a box plot where it does say as dot factor, fish code down here, and it has our weight column here, but now it's a factor for the purposes of this function only rather than character. So that only does it for the one function, only for making this box plot. As a permanent change for the R session, you can say, go in the fish data set and look at the fish code variable. We're going to overwrite that fish code variable by saying, right now, this is a character. Characters of all these 4-letter strings. And we want it to be a factor. So we're saying as dot factor, it's the same wrapper as was here in the one line of code. As dot factor, fish code. So we're saying take the fish code column, fish $ fish code, make it a factor and write over the fish $ fish code column. So this is just going to overwrite that column in the data set and make it a factor. So one caveat to this is if a column is read as a factor and is supposed to be numeric, you need 2 wrappers. So we talked about this in the intro to R, about the weird numeric character wrappers. If it's read in as a factor and it's supposed to be numeric, you need the 2 wrappers. Otherwise, the data are going to change to numeric based on ranks. For example, a character list of 0, 5, 17, 19 would be coerced to 1, 2, 3, 4 because it's ranking the data if it was changed to numeric from being a factor. To preserve the 0, 5, 17, 19, which are the data we want, when converting to numeric, we have to do the following. So this would be if we hadn't already specified weight as a numeric variable, then we could do this. So let's say we're just reading in the data here. And we're going to just select some of the variables. We'll look at what this pipe is in the next module, but this is just saying we're just paring down this data set right now to make it a little bit more manageable instead of those like 89 columns. So now we have 10 columns. We read in that data without specifying weight as a double or numeric variable. It's read in a CHR, a character. So if we want this to be numeric and we didn't specify the column name and we need to coerce it, this is a way to look at the structure of the data set over different variables. Again, we see character here, our weight column. We can coerce it using this as.numeric. Fish, the weight variable, fish weight. NA is introduced by coercion. Cool, we coerced it. Now we can look at that variable and say it's numeric and it's 1 NAs, etc. It did what we wanted. But if it read it in as a factor, for example, and this is where we're getting to, if we read this in as a factor, we have to say fish weight as dot numeric with an as dot character wrapper. Fish weight here. We have to convert to a character first. It was a character here, and we could just use the as dot numeric. If it's a factor, convert to character first, then convert to numeric. Otherwise, it will rank the data and will not keep the original values. And you do not want that. Okay, so that's an aside. Very important though, because I've run into so many issues with like people I'm helping code, my own code, and it's just something I really like to harp on is if you're coercing things, really look at what's happening. So before we manipulate the data, it's always a good idea to look at your data. Just use the str function. There are many different functions to look at the structure of your data. And each variable has some sort of class like numeric, character, formula, string, factor, whatever. This is mostly a review from the Intro to R tutorial, but it's very important to look at your data once you import it. So we're using our fish data set, and we can look at dimensions of it. 4,809 rows, 10 columns. We can look at the length of one of the variables. So the length of fish weight column is 4,809. That's exactly how many rows we have. The str of fish means structure. So look at the structure of the variables. We have some characters, numeric, characters, numeric. It tells us it's a tibble with 4,809 rows and 10 columns. Glimpse is similar to structure, but it's a tidyverse function. And therefore it uses DBL for double instead of NUM for numeric. Double and numeric are the same thing. I like the way Glimpse looks a lot better than structure. It looks a little bit cleaner to me than structure. It's just whatever preference you have or whatever you can remember. If we do summary, it gives you things like the class, the mode of each variable, the length of it, so how many rows there are. If you have numeric data, it's going to tell you the minimum, first quantile, median, mean, third quantile, max for all of them. Tell you character, mode, etc. Fish code here is a character. If we changed and coerce it to a factor, we can look to see that it tells us now, instead of having a character tells us it's a it doesn't tell us it's a factor. It just gives us the breakdown by factor. So for bullhead minnow here, we have 291 individuals, bluegill 748, etc. If you have factors, it breaks it down by sample size for those factors. Names provides the names of the columns. Because R is case sensitive, this is really helpful because you have to write exact case, like type case in your function. So you have to have the correct capitalization, correct underscores, periods, etc. Head shows the first 6 rows of your data. First 6 rows. This just gives you a glimpse of what your data looks like. Tail is the last 6 rows. View with a capital V opens up your data in a new tab up here. It's the same as opening your environment and clicking on the data set. It'll open it up in the tab. It's the exact same thing it does. Slice selects certain rows of your data. For this one, we specified the data set. Excuse me. And we say comma, we want to look at the first 10 rows of data. We use 1:10 to look at the first 10 rows. The colon means through. So we're slicing the data to look at the first 10 rows of data. That's exactly what it gave us. This second version of slice selects the first and 10th rows of data only because we have a comma in between rather than the colon. So this is the first row, this is the 10th row. That's what it's giving you. Slice can be really helpful in functions as well if you're just taking a subset of your data. All right, so view your data when you import it to make sure it imported correctly and it looks fine. Unique. Unique is a handy base R function. I highly recommend using unique. It shows you all the unique values in a column of your data set. This function is helpful for finding character or factor categories that might be duplicates because of capitalization or spelling errors, or when trying to filter results and you want to know the exact variables and their spellings in the data. So this is kind of like names to get the column headers, but this is to get unique factors within a column. So you say unique, name of your data set, the $ to get at the column name, which is fish code for species here. It spits out the unique values for those species in our data set. We've got 6 different species. That's how you spell them. Okay, now we're going to get into the dplyr functions. Arguably, these are the most commonly used functions in R because we spend a ton of our time wrangling our data into a format that's usable for visualization and analysis. So using these functions is crucial to understand. We're going to be filtering, selecting columns, creating new variables, renaming things, getting out distinct rows. Like, these are so helpful and they can be strung together. These are some of the most common ones. There are a lot of other ones as well. Check out the dplyr webpage here if you want to look at more variables. So the commonly used functions we're going to be talking about are distinct, which selects your first occurrence of data. Rename renames your columns. Select selects certain columns. Filter filters rows for some sort of specification. Arrange sorts your data. Mutate adds new data manipulations and keeps old data. Transmute adds new data manipulations, but only keeps the new data. Group by groups your data, and summarize is summary functions. We're going to look more at group by and summarize in the next meeting because group by itself just groups your data, and it's much more powerful if you use it in conjunction with other functions here, but we have to learn the pipe for that, and that's the next module. So we're going to go through each function, but we load the package first. So if you already have tidyverse loaded, just use the tidyverse. Otherwise, this is specifically the dplyr package. If you need to install it, uncomment that and run that code. Distinct. So distinct allows you to keep only rows with a unique combination of data. For example, if you have multiple rows with the same fish ID and you only want to keep one row from each fish ID to determine your sample size of unique fish, you could use distinct. So we're looking at our fish data set. Within our fish data set, this vital rate barcode is the unique identifier. And maybe we want to know if there's multiple rows that have the same vital rate barcode here. So what we can do is say, for every single one of these functions, it's the name of the function followed by your data name. So look in our fish data set, comma, we're just using distinct on the vital rate barcode column and a comma. And then if we want to keep all of our other columns of data, we say dot keep underscore all equals true. So instead of having 4,809 observations, we have 4,804 that were unique or distinct. So that means we had some duplicates for the barcode here, and that's something we might want to look into for that. If we don't put this dot keep underscore all equals true and we just do distinct vital rate barcode, it's just going to give us the vital rate barcode that's distinct. It's not going to give us our other data. So either they can be useful in different ways, but I like to keep all my variables because I'm just trying to remove duplicates, for example. The distinct function can also be used to remove duplicate rows. If for some reason your data duplicated itself or you got data from someone and you're like, okay, there's a lot of duplicate rows in here, like completely duplicate rows, use just distinct on your whole data set. So distinct fish. We don't have any completely duplicate rows. It's still 4,809 rows here. It was just the vital rate barcode that is duplicated. Okay, the rename function changes the names of data columns. And I want to note here that when we're going through the coding, before we talk further, that no function, not just dplyr, nothing saves your results unless you save your changes as an object with object name and the arrow. Here we were just running a function and it spit out the code. And this is for example only. It is not saving over the data set. It's not creating a new data set unless we put fish there. And then we would save over our data set. So now our data, if you look in the global environment, has 4,804 observations instead of the 4,809. You have to save over if you want to save something. A lot of this I'm just doing for example, so I'm not saying save over the data set, which I think is perfectly fine to do. To create a new object, you just name it a new thing. So fish1, for example. To write over the old object, just make it the same name, fish. So rename changes the names of data columns. Rename the name of your data set, fish. The new column name equals the old column name. So fish code's not a very intuitive name for species. So here we're going to change the fish code column name to species. Here shows the output species instead of fish code, and it's a factor. Again, this does not save this in the data set. If we look at the fish data, it goes back to fish code because we did not save it using the object and arrow sign. So here we are saving it, and this is a way to rename multiple columns. Rename, specify your data set, comma, concatenate function, which is just C, parentheses, species, new column name, equals, old column name, fish code here, comma, maybe you want to capitalize weight instead of having it lowercase. So make it capital weight equals lowercase weight. And maybe we want this to specify that's total length, TL equals length. So we're just changing those column names. And if we look at our names, we now have species, TL, and capital weight here. The select function selects columns of your data. So for example, we want to select just the species column. And here we're going to save it as an object called species. So species, arrow, select, specify your data set, specify the column name you want, species. And if we look at this in the View tab, it's literally just a column of the species column. That's a new object. You can also select multiple columns. How about species and total length? All right, we're naming a new object, species TL. Select, specify your data set, comma, one column you want, species, comma, total length. Specify our two columns we want. And if we look at this, we have just species and total length here. I'm not sure why you don't need the concatenate function here to just be like species, total length, whatever. And you need it in things like this to rename. But hey, nuances are nuances. All right, this one, like you don't need to have the concatenate, but you can. So this is select, specify your data set, C, or concatenate species and weight. Here we need that to rename. Here it's optional because you can just specify them with multiple commas. Here you see either one works. Species and weight. We're going to get species and weight. Select fish is our data set. So specify your data set. This is selecting all columns in between species and weight using the colon. So select all columns, including species and weight. Species through weight columns, which gives us species by every barcode, power used, volts, amps, total length, and weight. Gives us everything that was in those columns. You can also select columns by number. So if we look at our fish data set, column 2 is S date, column 3, 4, 5. This 2 through 5 is going to select columns 2 through 5. So S date through vital rate barcode. That's exactly what it did here. This one, select, you can do a combination here. Specify your data set, concatenate. We want the first column, we want the third column, and then we want columns 4 through 7. So that should look like the first site. Field station is the third, and then we want species through column 7. So 4, 5, 6, 7, species through volts. That's what we get. And again, look at the names of your variables if you need to know their exact spelling here. I do want to point out that you can mix and match numbers and column names. So you could say, we want site, and we want F station, and then we want columns 4 through 7. And it's going to give you the same thing. And you can use numbers, you can use column names, you can do a mixture of the two. There's also quite a few Boolean operators you can use with select to get certain columns. So you can use things like starts with J, so select columns that begin with J. Ends with BR, select columns that end with BR. Contains OCT, select columns that have OCT within their name. Matches some sort of pattern, x.1, so it would select columns that are like x.1 where the X is the column name. So it might be like species.1, total length.1, weight.1, etc. And then number range. This would select columns matching x1, x2, x3, where you're saying this is the pattern to look for is x. And the variable names are 1, 2, 3 with that. So x1, x2, x3. Those are a lot more complicated than just starts with, ends with, or contains. So for example, we want to specify our data set. It ends with QF. There's nothing there because it's in the original data set, not the smaller data set. So if I read in the original data set here, instead of the one we've been working with only 10 columns, we can look to see what this looks like. So select our fish data set and we look at fish, has our 86 columns in it now. Fish ends with QF. It gives us all 11 columns that end with QF. VQF, AQF, PQF, etc. No clue what these actually mean. It should be in the metadata. I've not looked at that. But it's a repeated pattern throughout the data set. You can also rearrange variables in your data set using everything. If you want your data columns to look a certain way. For example, maybe if we're looking at our data, we want the species to be in the first column. Here, because we didn't rename this, we'll rename that a second. We can select fish, and we want species to be the first column, and then we want to keep all the rest of the data, so let's just say everything. Now we have species as the first column rather than like the 75th column or whatever it was. So it's upfront what our columns are referring to. You can also deselect or remove columns. So select. Maybe we want to remove the species column for some reason. Specify your data, put a minus sign in front of the column name, species. So now we have 85 columns instead of 86 because it removed the species column. You can remove multiple columns. Here we're removing from the fish data set, species, weight, and total length. You have to put a negative sign in front of all of them. And we have now 83 variables because we removed 3 of them. And if we want to remove all columns between and including things like remove power used through amps in our data set, we now have 82 columns because it removed everything between those rows. So that's just a way to look at this. To remove and keep specific rows. So filter is the next function. I find filter to be probably one of the most helpful ones because it allows you to look at subsets of your data. It selects rows based on some sort of specification. Something like you can select certain species, you can select a volume size, certain length, a certain date, a certain weight, etc. So for example, here we're going to filter by a single variable. We're creating a large data set. Maybe you want to just look at large fish. We arbitrarily say anything greater than half a meter, so 500 millimeters is a large fish. Filter as the function, specify your data set, comma, then your operator. We're looking at the total length column and we want that value to be greater than 500, and that's arbitrarily our large fish. If we look at our data set, we have 246 rows. That's a lot fewer than the 4,800 that are in this data set. And we could look at a histogram of this data set and just know, cool, everything's 500 or more millimeters. It goes up to 850 there. Let's say we wanted to just get a catfish data set. So we can name an object catfish, filter, specify the data set as fish. Our species here is catfish, which is CNCF. When you are saying something equals in filter or in anything, mostly just filter, but other functions might use this too, it's equals equals. It's not just one equal sign, it's two, because a singular equal sign means something else. Equals equals, and then your factor character must be in quotation marks. It's going to get us channel catfish. We look at this data set, very large data set again. Species, only CNCF for channel catfish. That's all we need. That's what we told it to do. So that's looking at one variable specifically each time. We're creating a catfish data set, we're creating a large fish data set. You can use a lot of different qualifiers to look at filter, and you can filter by multiple columns. So you can use the greater than, the less than, the greater than equal to, less than equal to. Not equal to is exclamation point, equal sign. Equal to, remember, is equals equals. Near can sometimes, you can sometimes run into problems with equal equals. So R likes to round things. So if you have like zeros, or what R tells you are zeros, but they're actually like 0.00001, near can help with that. Between, so things like we want total length between 200 and 500 millimeters, for example. And then you can, values that are not NAs is exclamation point is dot NA. If you wanted NAs, you could say is dot NA only without the exclamation point. You can also use multiple Boolean operators if you want to filter for multiple results. So you want Y, but not X. You want X and you want Y. You want X or Y, or you want multiple factors like including. We're going to look at these in more detail with examples. So we're going to practice with a couple of these Boolean operators for filtering out multiple things. All right, we want to look at our species again. Get our unique out. 6 different species: bullhead minnow, bluegill, channel catfish, emerald shiner, freshwater drum, and gizzard shad. Maybe we want to create a data frame of just forage fish, which include emerald shiner, bullhead minnow, and gizzard shad. We can use filter in multiple different ways. We're going to use 4 different ways to get to the same exact thing. So filter, we're saving this as object forage. Filter, specify your data set as the fish data set. We want the 3 separate species. So we need species equals equals emerald shiner. Or, here we have the or, which is the vertical line. Species equals equals gizzard shad. Species equals bullhead minnow. We run this and look at our data. We have 1,950 rows. Okay, or yeah, rows, and then our 86 columns because we didn't remove any columns. Cool. And unique for our species, we have just our 3 species. That's exactly what we told R to do. Another way to do this is to say we don't want the other species. This is remnant of having extra fish in here we didn't want. So just remove those. Same with down there. Okay, we don't want the other 3 species. So filter, specify our data set. Species does not equal channel catfish. And species does not equal bluegill. And species does not equal freshwater drum. Look at this, glimpse it, 1,950. or unique species, just the 3 we wanted, by saying we don't want these other species. The nuance here is that if you are specifying the species you want, you have to use or in between, because there are no species equals emerald shiner and gizzard shad and bullhead minnow. It's species of emerald shiner or gizzard shad or bullhead minnow. Whereas if you do not want the species, you say we don't want channel catfish, and we don't want bluegill, and we don't want freshwater drum. That's the nuances. And for no's, or's for yes. This is the one I recommend using, is the %IN% for including. Filter, specify your data set as fish. Say your species, whatever column you want, including %IN%. Concatenate, and then just list out in quotation marks what variables you want. Emerald shiner, gizzard shad, bullhead minnow, just in a list. You don't have to then say species equals or does not equal CNCF and species doesn't equal this, because you have to write it out every time for these. Where this, you just put the column up front, say including, concatenate, and all of our variables we want. Okay, forage 2, 1,950 rows, and the 3 species we want. And then finally, the other way to do this is to say filter, specify your data set as fish, does not include species. Put an exclamation point in front of species, including the 3 species we don't want. Glimpse, 1,950 rows. Unique are 3 species we did want. So those are 4 different ways to get to the same exact filtering of the data for a forage fish. Choose the one you are most comfortable with, that makes the most sense to you, and move forward with that. But there are many different ways to do the same exact coding in R, which I think is awesome, but also frustrating. All right, so we're just looking at one column so far with these Boolean operators, but what if we wanted to filter based on 2 or more columns? So to filter multiple columns, maybe we'll create an object called catfish2. We want to filter our fish data set and make sure total length is numeric. You can do a wrapper here. And we want total length to be greater than 500. And we want the catfish to, or we want the species to be catfish. So we want large catfish specifically. So total length is greater than 500. Cool, we did that already. So we got the large fish. So that's the same exact code as that. But now we want it to also include that these are only channel catfish. So it's and species equals channel catfish. You look at this, glimpse, 216 rows. We can, where did this go? I don't know why that like jumped really far. Okay, we have our total length. We have our species of our fish data set. Cool, we've got all of our species out there. We plotted this just for our catfish2 data set. We just have the catfish now and our total length. It's exactly what we wanted. This is how you check your data. Look at your data for the whole data set versus your subsets, and you can check your data that way. We have large channel catfish here, greater than 500 millimeters. Here we use the and because we wanted both these species to be large, so greater than total length greater than 500, and we wanted to be channel catfish. We could say or, then it would be large or channel catfish. So if we look at those data, we have 1,283 individuals because we have all channel catfish and we have the large individuals. So just think about what you want in your data set, if you want large catfish or if you just want catfish and large individuals, because that is different with which operator you are using, the and or the or here. Okay, sometimes you want to separate NAs from your data from the rest of your data. And it's easiest to use the is.na along with a filter to do so. So for example, we don't want weight data that has NAs in it. And this is going to remove all rows completely where there is an NA in the weight data. So really think about what this is doing to remove those NAs before you actually do it. Filter, specify your fish data set. Exclamation point is .na, so not NAs in the weight column. We have 3,484 rows now. So there's like 700 fish with missing weight values. We could also just look at is NA and get the opposite of that is the 1,325 individuals that have weight values. I guess there's this this is how many, not 700, that have missing weight values. So that's quite a few of them is to be missing weight. So if we removed all those fish from analysis, then that's a lot of fish we would be missing information on otherwise if they're just missing that weight data. So just think about what those NAs are and if you wanted to remove them or not, or just see how many NAs are there in this data set. So this is an example of using the between function to keep all records between two values or exclude records between two values. So here we're using, this is the same as using greater than or equal to or less than or equal to for the bounds. So for between, for example, we want to say we want to filter fish between total length, so specify your column name here, of 400 to 600. So if we look at our histogram, we only have 400 to 600. This is within that data set. Maybe we're looking at slot limits or something here. If you don't want between, or protected slot, removing fish, filter, specify your data set, exclamation point between, total length of 400 to 600. Histogram not between, we're missing 400 to 600 because we said don't include those, so it's everything else. Just a way to look at your data. And then finally, some filter combinations. There's a few nuances I want to stress when filtering and switching between or among and or including, etc. It's basically order of operations and common sense govern the way the code should be written here. So for example, we don't want to just have our forage fish, but we only want to select maybe a couple of our field stations in this data set. So F station means field station here. So maybe you want to only look at pools 4 and 8, which are field station 1 and 2 in this data set. So what we do is we say, okay, we're going to use filter because we're subsetting the data. Specify your data set. For the species, this is exactly what we did earlier. We're saying species including emerald shiner, gizzard shad, and bullhead minnow. Cool. And we want the field station including 1 and 2 for those field stations. For species, we've got our 3 forage fish. And for field station, we have field station 1 and 2. That's exactly what we wanted. This is the easiest way to do it, and the one I would recommend is using the includings. If you are using something else, there are more nuances. Okay. Percent including and the or sign. Filter, fish species. We want our species to be these 3. And maybe we don't feel like doing the percent including percent again. So we say and field station equals 1 or field station equals 2. And this and is surrounded by parentheses. Parenthesis here, parenthesis there. What this looks like is we have our 3 species because we use the including. And We have our two field stations because we used parentheses here to say we want these species and we want the field stations to be 1 or field station 2. Awesome. If we don't do those parentheses, this is the same exact thing, species including these 3, and field station equals 1. Okay, that makes sense. Or field station equals 2. This is literally just missing the parentheses around the field station 1 and field station 2. All right, if we copy and paste this, we have all 6 species in here. And we have our 2 field stations. So why do we have all 6 species in here? It's because R is saying, yes, include these 3 species and field station 1. So these 3 species are coming from field station 1. Or everything from field station 2. Because there's no parentheses around here to say, do this and include only 1 or 2. We want everything from field station 2. That's what that's saying, while this parentheses around here is just saying, select these 3 species and select these 2 field sites. So be really careful with this. And then finally, if we don't use the percent, including percent here, we say we're putting our species here, we want all 3 species. You have to put that parenthesis around them and the parentheses around here to denote the correct species and field stations we wanted. So species here are 3 then, and field station 1 or 2. Whereas if we did not have any of those parentheses, we get something very different. We get all 6 species, and we'd have all 6 field sites because it's saying we want species equals emerald shiner, or species equals gizzard, or species equals bullhead minnow, but make the bullhead minnow only from field station 1. Or we want everything from field station 2. It's very different. So remember those parentheses, unless that's what you wanted to do, is get something wonky like that. So think about your parentheses and whatnot. One of the other things I found really useful is filtering for character strings. So sometimes you want to filter for character strings such as like specific year and a date column, a specific month, or other common strings. It's very easy to do this with the select function because you have the starts with and ends with qualifiers. But you can't use starts with and ends with filter. You need arguments from the stringer package instead. So, for example, we'll use this to filter everything with the barcode that starts with VR1. If we look at our data set, we have our barcode. It's probably at the end. Vital rate barcode, we have VR1, and it goes through VR6, VR2, VR3, VR4, VR5, VR6. Maybe we just want the VR1s. So we're saying specify our fish data set. We're using this grepl or grepl function to say, okay, this is a pattern matching function. This is our pattern in tick marks or single quotations or whatever you want here. Our pattern is VR1 from the column vital rate barcode. And we're going to name this fish1 to look at our data. Our fish1 is 581 individuals, so a lot smaller than the 4,800. And our vital rate barcode is VR1 throughout the whole thing. So it took that pattern matching and filtered for that specifically. This is how you do that. Cannot use the starts with and with. You have to use this grepl or another function similar with filter specifically. Okay. Filtering is probably the most extensive one in here because there are a lot of nuances with filtering, and it's one of the most common variables, common functions to use. So next, we're getting into arrange, which is just sorting your data based on some sort of specification you want. It defaults to sorting in ascending order, so from smallest to biggest, but you can add an argument to sort descending. So for example, arrange fish based on total length, ascending order of total length. So if we look at total length, scroll over to that, we now have the smallest individuals at top, and it'll increase as we move down. Larger individuals here now. We arrange descending order of weight. Specify your data set. DESC for descending, and then your column name. So if we look at the weight column, we now have the largest, the heaviest individual at the top here, 7,228 grams, and then it descends as we move down those columns. Mutate lets you create new data columns using the data you already have and tax that onto your data set. So this is a really easy way to calculate summaries, totals, multiply data columns together, anything we want. So for example, maybe we want to create a new column of total length that's in centimeters instead of millimeters. So we can say mutate, specify your data set, create the new column name of total length underscore cm for centimeters, and that equals the column total length divided by 10. So if we look at this data set, tax it on at the very end, we now have this new column TLCM, which is 5.4, 4.2, which is just total length divided by 10 here. We can use multiple columns in these mutations. So something like mutate, specify your data says fish, PWR for power equals amps times volts. So we want to say the power column is just amps times volts. When you're electrofishing, we want to look at power specifically. And here we're going to select, because there's already a power used variable in here to make sure it did it right. Power here, they are the same exact value. This is just to show that it is doing what we did or what we told R to do, where it's multiplying amps times volts together, because that's how this power used column that was already in the data set was calculated. And then we can arrange, we're just going to delete that. What that's from. Okay, so that's how you look at your mutate there. So you can get a lot more complicated with mutations. One of the things I usually do is calculate percentages or proportions with mutations. So this is a way to do that. So mutate, looking at our catfish 2 data set, which was the large catfish, we can say percent weight, or our catfish and large individuals here. Our percent weight equals the weight column divided by the sum of the weight column. So for finding percentages, it's a value divided by the sum of whatever's in that value. Here we have to say NA.RM equals true as an argument because there are NAs in the data set. And then to get percent instead of proportion, it's multiplied by 100. So we're using the weight column, a function to calculate the sum of the weight column, and then timesing by 100. So this is going to give us a new variable at the end of this data set, percent weight. This is the percent of the total weight that each individual constitutes. So this first individual constitutes 0.38% of all the catfish by weight. This one, 0.4%, etc. You could look at species diversity with this. You could look at percent sample size, like anything you want with mutate. It just creates a new data column. Transmute, conversely, it does the same thing as mutate, but it doesn't keep all your old data. It's not just tacking on a variable, it's just producing the new variable. So transmute, specify your data set. We're going to go with our standby of power and total length underscore centimeters. So we're saying power equals amps times volts. And total length underscore centimeters equals total length column divided by 10. So if we look at this, it literally just has the two new data columns in it because it just makes the new data columns. It does not tack it on to your old data. And then finally, summarize allows you to calculate summaries of the data, which can be really helpful for graphing general summary stats for a table or anything like that. So summarize, specify your data set, fish. What our summary is going to be called, mean total length equals, it's the mean of the total length column. Mean W for mean weight equals the mean. And here we're trying to remove those NAs, so we can say exclamation point for is not, is dot NA weight. This is the same exact thing of saying weight NA dot RM equals true. It's just a different way to say it. It's removing those NAs. Either way works. Again, the theme of R is that there are multiple ways to do the same thing. So if we do this, it's giving us a mean total length and a mean weight for the entire data set, which, I mean, we could have done this much more easily. We could have said mean fish $sign total length, and it gives us the same value. That's much more simpler than using the summarize function. The power behind the summarize function comes with group by and using the pipe, which we are getting at in the next module. And therefore, we will see how powerful this can be and how useful it is, because I use summarize and group by all of the time. So that'll be the next module specifically.